All right. So today we will discuss this. This thing is factor group. I don't know why I'm writing it. Anyway, this is factor group Q over Z. Now, I've been waiting for at least 20 days to make this video. I thought I would read some more theory about this group and then I will make a video. But I realized that that is not going to happen. Also, I'm aware of most of the theory. So if somehow this group is thrown at me, how am I supposed to decipher it? Well, let's do that. Let's see how it goes. Also, I lost a few marks because of this, so I'm pissed at this group. Anyway, now what can we tell about this group? First thing, what to tell about Q is the set of rationals over addition a group. I guess that is right. Yes, it is. It is not a group under multiplication. The reason being that 0 belongs to this set and 0 does not have a multiplicative inverse. So this thing is not a group. This is a group. Okay, now I have discussed this factor group in another video. Or there are other videos, just check that out if you don't know about it. There's no point watching this video if you don't know about factor group. So you can skip, learn about this, and then come back to this video. And there are dogs now barking. Anyway, sorry for that. So Q over Z. What that means is that I separate this subgroup from this group. That is the first thing I do. Then for Q over Z to be a group, Z has to be normal in Q. And Z is normal in Q. The reason being Q under addition is an abelian group, right? Rational numbers commute. So any subgroup that contains the identity any proper subgroup or even trivial group, whatever, any subgroup will be normal, right? So using that, we can be sure that Q over Z do form a factor group. If Z was not normal, we would not get this group. Yeah, I think, I think that is the case. Correct me if I'm wrong, of course. So Q over Z. Now, what are the elements of Q over Z? Now, I have discussed this. I have discussed this earlier as well. That this group, this looks nothing like this original group, the group of rationals. This group, the identity element of this group is the subgroup itself. My Z looks like 2. Is this subgroup itself? And then, what are the other elements? Other elements are of the form A plus Z. Plus is the operation which was on this in this group, right? A plus Z, where A belong to Q and R not I mean A are strictly rationals. Strictly rationals means it does not make any sense. Z minus Q or Z by Q by Z. This type of elements are A, because if A is an integer, you know the property of a subgroup, right? Normal subgroup, like if we operate an element, like if I take B that belongs to Z and I operate B with Z, operating as in I'm finding the left coset in this case. If B belongs to Z, then this will be equal to Z itself, right? So if A is an integer, then this process is redundant. We'll get this back. I think I over-explained this. It was unnecessary. But anyway, so yeah, A does belong to rational, and I think that is sufficient. See, the purpose of this video is to clarify the concepts. I might skip some point which is very trivial to the definition. I might not write it. I will use it, but I might not write it. So take these videos with a pinch of salt, I guess. So yeah, this is Q over Z, right? Now, what I want to identify is what will this Q over Z be isomorphic to? Is it isomorphic to Z? Or is it isomorphic to Zn? Or is it even finite? What can happen, right? Let's explore this, all these possibilities. Let's explore them. See, so first let me take a random rational number, right? Let me take P over Q. That is too vague. Let me take 7 over 9. That is too lengthy. Maybe, okay, let's take 2 over 7, right? Now, if I start finding, if this is an element, 2 over 7 plus Z, then what is the order of this element? Okay, see, for isomorphism, how do we know if they are isomorphic or if they are not? The first thing we can do, or we should do, is that we should check the cardinality of these two sets. If the cardinality is different, then they cannot be isomorphic, right? And now, yeah, let's actually see what is the cardinality of these two sets. See, A, this set has all the elements belonging to rationals. Okay, rationals are countable, integers are countable, so the cardinality is same. That is not an issue. Okay, what about Zn? Zn. Oh, we'll look at it later, right? Let's just focus on this now. So this was an element from the group Q, and now I'm operating it. So what shall be the order of this element? Interesting. Okay, so the order of this element is how many times I need to operate this. I am assuming you're aware of this. So I'll just use it. 2 by 7 plus, see, a plus z operated on, let's not use addition here, operated on b plus z, b plus z. This is same as a plus b plus z. If you find this confusing, go back to some video of vector group and this thing will be pretty clear from there. So now 2 by 7 plus 2 by 7 plus 2 by 7 plus 2 by 7. How many times? Actually, what I'm trying to do is I'm trying to generate an integer here so that I get my identity back. See, this group, this subgroup, this denotes the identity element of this vector group we are dealing with. So how many times do I need to take this to generate an integer here? Obviously 7 times, right? Plus 2 over 7, 7 times. Because what that will do is, it will give us 7 times 2 over 7, which is 2. So we will be getting 2 plus z, which will be z itself. So order of this element is 7, right? So this was a very specific case, but if we take any random case, p over q, and if we add this rational number q times, then we will generate a q here. This will cancel out and we will end up getting an integer here, right? So what was the purpose of this? The purpose of this was to ascertain that every element in this set will have an order equal to the denominator, right? And what are the options for the denominators? Q, which is the denominator, can belong to the set of integers, which is itself uncountable. So we have uncountable choices for Q, right? We have uncountable choices for Q. What that means is that we already went over this. This thing defines the cardinality of this set. Again, I'm sorry if this is confusing, because this is confusing, okay? And it's unstructured, so I'm just brainstorming. So Q is the thing that will give us the number of elements in this group, and Q belongs to integers which are uncountable, which are countably infinite, and so is this set. They're isomorphic, Q and Z. I mean, this is Z itself, right? So basically what we figured out from this thing, all of this, was that the cardinality is same, right? Let's look at the elements of these two individual sets. I mean, this was okay. We looked at an element 2 by 7. Now let's take a look at an element 2 belonging to the set of integers. What is the cardinality of 2? Or no, cardinality is not the right word. What is the order of 2? Infinity, right? You can operate 2 anytime, any number of times. 2 plus 2 plus 2, any number of times. We are never going to get 0. There are only 2 elements in this set which have a finite order. Are there? No, there are not even two. There is just one element of finite order, and that is identity. No other element in this set is of finite order, because remember, the operation is addition, not multiplication. So 1 square is 2, minus 1 square is minus 2, right? What this implies is that this set has only one element of finite order. However, and that one element is identity, right? That is of order 1. However, in this factor group, obviously identity element will have a finite order. It always has, and that order is always 1. But we found another element of finite order 7, and we will find many elements of the order q, where q can be any integer, right? Any positive integer, I should say, right? Yeah, we can accommodate negative sign in the numerator. Yeah. So isomorphism is out of the way. Okay, like this is not isomorphic, because we just proved that there are more than one elements in this group which have finite order, which is not the case in this set. Okay, and now let's evaluate Zn. Let's see what happens here. I don't even know what I marked in my exam, not exam, like a test, but it was something like this. Either, yeah, anyway, let's not dwell on it. I'm telling this to myself. So QZ and Zn. Now, this is interesting. Zn is very vague, so is QZ. So, well, yeah, it is, after all, abstract algebra. So I'll let them be vague. Okay. Now, okay, for understanding purpose, let's take n as 1000. Okay, just a random number over the top of my head. And let's take a rational number, not 2. Let's take 3 over 1000, right? Yeah, seems fine. So what about Z1000? Well, oh my god. Yeah, see? Z1000 will have 1000 elements. Cardinality of the set 1000. Cardinality of the set has already been established. It is LF naught, right? If you are aware of the symbol, good, right? But for simplicity, these are just countably infinite, right? That is the cardinality of this set. Now, Zn, even if, see, even if n was an abstract figure, an abstract value, what is the possibility of n? Then we cannot rule out. Let's say n is approaching infinity. Then, okay, let's say n is approaching infinity. Then these two elements, sorry, these two groups will have same cardinality, right? Yeah, I don't see anything wrong with that. Okay, so if n approaches infinity, for a specific value, for any specific value, they will never be isomorphic. But when n is approaching infinity, to be honest, I haven't seen this concept yet in any book where we establish the cardinality like this, but whatever, let's just get it out of the way. Okay, so we are doing this. If n is approaching infinity, then the cardinality uh, is same. Okay, so now to prove isomorphism, we will need to look at other things. The next thing that comes to our mind is the order of elements. Now, if n is approaching infinity, even if n is approaching infinity, it will obviously have 0, 1, 2, 3, and so on till n, where n is approaching infinity, right? So this set will contain these elements. It is an infinite set. Similar will be the case with this. This set will be p over q plus z and z identity, of course, identity, and this such that, my bad. Okay, we already established that q belongs to z plus and p belongs to z. It is just a distinction we are making, nothing specific in that. Okay, because I'm using q as what do you call it, as a reference to establish the cardinal order of element. That's why I'm taking it positive. Okay, anyway, and now I'm wondering that this video might be very confusing for the viewer. If that is, I apologize, but I needed to make this. Anyway, so P over Q. Now let's look at the order of these. Since n is infinite, order of an element, see, every element will have finite order. Is that so? No. If n is approaching infinity, n can be an even number or n can be an odd number, and we cannot even establish that. But we can definitely rule out the possibility that if n is even, then if n is odd, then there will be no elements of order 2. Yeah, it is impossible to establish the order of elements in this set. In this group, it is a group, Zn is a group, but it is only defined when n is finite, right? That is why we call Zn a finite group, and we call Z an infinite group. Right. Okay. Okay, so let's turn back everything. N is not approaching infinity, and say n is a finite value. Now what do we have with us? Since n is finite, if it is finite, let's give it a value like before, 1000. And yeah, we already established that these are not isomorphic. Right. So this is also not isomorphic to this. And what mistake I did was that I don't remember. Okay. But okay, what about a subgroup of this factor group? A subgroup will contain the identity, and then we can have a subgroup generated by this, sorry, slight mistake, Z and plus Z, where P belongs to integers. This is a subgroup, right? For simplicity, let's even give P a value. Let's give P a value of 7, right? This is a subgroup of our factor group, right? Is it? Yeah, it is. It is a cyclic subgroup indeed. of order 1000, right? So will this be isomorphic to Zn? Uh, I can't see why not. Well, will this be isomorphic to Z1000? Any finite cyclic group is isomorphic to Zn, yes. And this is a finite cyclic subgroup of this. So yeah, I think these two are isomorphic. Yeah, there's no doubt about that. So a subgroup of this can be isomorphic to Zn, but this entire group will not be isomorphic to Zn, right? Right. Yeah, this is what I wanted to discuss with myself. So anyway, yeah, I think that is all, and I'll end this video. What was the point of this video? Well, you get to understand, and I also, like, we get to understand that if a random group is thrown at us, how do we look at its elements, considering the operation, and how do we establish isomorphism with other groups, right? Right now, I want to establish or just check to which group this is isomorphic to, but I don't think I I don't think like that would take a lot of time. Let's just, I'm tempted to now. Let's just Q over Z, right? Let's just see. Uh, okay, let's just define the elements. We have already defined it 1,000 times. I mean, a few times. So P over Q. And what are the type of elements in this? Well, it has infinite elements, and it will it has elements of infinite order, because rational numbers are themselves infinite and this place is occupied by rationals. So this is a group. This vector group is a group. Is it, if we have P by Q plus Z plus R by S, take this plus as operation, composition plus Z. This is okay. Yeah, this shall be an abelian group. This is the variancy. If we reverse the order and then add or then operate, we will get R over S plus P over Q. And rationals are commutative over addition, even multiplication, right? So, okay, this group is abelian, obviously not cyclic, because there is not one single element which can generate all the elements. Yeah, and we already proved, right? Because if it was cyclic, then it should have been isomorphic to Z. Is it cyclic? Yeah, Z is a cyclic group, one is a generator. Can one generate all the elements? Okay, so this is abelian non-cyclic group, and infinite order abelian non-cyclic infinite sounds like the group Q itself. It is abelian non-cyclic infinite order, has subgroups, cyclic subgroups of finite order, and has infinite such subgroups, just like this. Like if Q is 1000, we can take Z 1000 not equal to like a subset, proper subset, and Z 1000. Yeah, it is a finite cyclic subgroup of this group. Okay, so does that mean Q over Z is isomorphic to Q? So far, I think yes, but I'm ending the video because it is quite long, and yeah, you check this. Or okay, I will trim the video if it is too long. I don't have a timer with me right now to see how long is the video gone. So discuss the let's discuss this. Okay, it shall be interesting and brainstorming. Second time I'm using this word anyway. So yeah, whatever the set Q, cardinality is same, right? Established. Cardinality check. Properties, both are abelian, both are non-cyclic. Okay, good. No need to write abelian and cyclic, non-cyclic. Yeah, like I said, no need to write abelian, not cyclic. So elements of finite order. Right? 2 by 3 plus Z is an element of the subgroup, sorry, this group, vector group, and it has order 3. But it is not the case in this set Q. They are not isomorphic. I'm glad I checked. It was so easy to establish this. Okay, Q has just one element of finite order, right? So we can't just jump into conclusions like I do at times. We need to analyze. We have the we have sufficient information at times, but we just are too stupid. At least I am too stupid to apply it. Anyway, right? So yeah, that's how we check isomorphism of vector groups. Specifically this one, I wanted to discuss this one. If you have other ideas, put it in the comment section. I will do that whenever I find time. And yeah, I hope you learned something from this video. I doubt that because that's why I said this. Anyway, I'll be ending this video. Any doubts or any mistakes, point it out in the comments.